Okay, now we have one more issue with the conjugate gradient method. As we said earlier, we can prove the convergence within n steps, where n is the number where is the dimension of the variable x. We know that it will converge within n steps if we have the nq conjugated directions. But the problem is, how do we get these directions during the for the conjugated gradient method? We don't want to compute them in advance because, as we showed earlier, constructing them can be pretty expensive. We did one example for a 3x3 matrix. So the conjugate gradient method has a very clever way to get these conjugate directions during the iterations, and the computation of these directions is much cheaper than the one we did before. So here, this is how these conjugate directions are constructed along the way with the iterations. Now, as I said, we're going to show that the conjugate gradient method is going to generate the new conjugate directions in every iteration. And how are we going to generate them is, suppose we already have the xk, and we already have the previous conjugated direction, dk, and then we know that we can compute the next iterate, xk plus 1, using this simple update, where this dk is a search direction. It's used as a search direction, and this alpha k is the step size. As we showed earlier, we're going to choose alpha k to be this ratio. Okay, it's a scalar, which is inner product of two vectors. It's a scalar divided by another scalar. So this is going to be our step size. Okay. Now the problem is that now we get the new point, and we're going to update the xk plus 1 using the similar formula to obtain the xk plus 2. But to get that, we need the next conjugate direction, dk plus 1. And the conjugate gradient method tells us that we can construct the new conjugate direction, dk plus 1, using the previous conjugate direction. This is where you came from to get the xk plus 1. And once you get the xk plus 1, you compute the gradient of f at this new point, and that is the gradient, that's the gk plus 1. So the next conjugate direction is a linear combination of the new gradient we just computed and the previous conjugate direction. And the combination coefficients is there are the 1 here and this beta k here. And this beta k is said to be this. Okay, this beta k is different from the one that we used to prove the convergence of the basic conjugate gradient algorithm. So this is a different beta k, and this beta k is used to make this combination of gk plus 1 dk to get the next conjugate direction. So now you can see if this is working, then we don't really need to follow the example we had earlier to construct those dk recursively, and every new dk plus 1 is going to be q conjugated with respect to all the previous ones, which is very expensive. But now the update of this dk plus 1 is very simple. It's just doing this. Okay, so now let's see how this is going to work. Again, we're considering the quadratic functions first. Remember that we're focusing on quadratic functions, and that is also the reason why this alpha k can be chosen in this closed form. Is this closed form because that is the steeply descent step size for quadratic functions. Now this is our quadratic function, where q is positive definite, and then given the initial x naught, we can compute the gradient f at this x naught, and that's our g0 or g naught, and then we'll just set the first conjugated direction as a negative gradient, negative g naught. That is the negative gradient direction is going to be our first conjugate direction, and then starting from there, we can compute the step size used to update. So this is exactly the same step size rule we used earlier. So I'm not going to expand this more. And then once you have the step size, and you have the current x0 and xk and d0, and we have the d alpha 0, then we can get x1. Okay, and but in general, once we have xk, and we can compute the gk, and then we're going to update the dk and update dk using the previous formula, and then we can do this step. Okay, so now for now, you just think that we start from k equals to 0. Then, as we said, we compute alpha 0, and all we need are this g0 and d0, and which we already have g0, d0, this. Okay, and then compute alpha 0, and then we have x1. And once we got x1, we can compute this. We can compute this gk plus 1, or g1. And then once we have the g1, we can compute the beta 1. Again, on the right hand side, everything is known. And then once we have the beta 1, we can update the descent direction to get the new conjugate direction, which is also our descent direction. And now you can see after this step, we can get the d1, x1, and g1. And then we're going to increase k by 1, and k will be equal to 1 now. And then we can compute this alpha 1, then x2, g2, so on and so forth. Okay, so for each iteration, we're going to do these steps. Okay, we're going to do all these steps. Okay, so before we move on, let's first see what is the computational cost of this algorithm. Okay, we said that we're going to iterate this for at most n steps, and this is because of this algorithm actually generated this Q-conjugate directions, and we know that in this case, the algorithm should converge within n steps. So we're going to only run it up to the xn. It's supposed to give us the true solution. Okay, so the thing that is still pending is that why this is going to be a conjugate direction. That is something we're going to show later. But suppose this is true, and let's see that we're going to run this iteration for n steps, and for each step, how much computation we need. Okay, as you can see, to compute this alpha k, what I will need is a inner product of two vectors. And to make an inner product of two vectors, two n-dimensional vectors, we need to make n multiplications, right? Component-wise multiplications, and then we need to sum them together, which requires n minus 1 summations. So the inner product of two n-dimensional vectors requires so x, y, they are all n-dimensional vectors, requires n multiplications between scalars, and then n minus 1 summations. Okay, and then usually the multiplication is much more computationally expensive than the summations. Okay, often you can consider it as almost 10 times more expensive than summations or subtractions. So multiplication and divisions are like 10 times higher, or 10 times longer, takes 10 times longer than the summations. But although you will not usually notice that during the actual computations because they're all mixed together. But as you can see, what I'm trying to say here is that you basically have the same amount of multiplication and summation, but this multiplication will dominate. Okay, so that's n multiplications. So usually when we consider the computational cost, unless this is there are lots of summation subtractions. Otherwise, we'll just consider the multiplications. Okay, and here, as we said, we have inner product of two n-dimensional vectors. So this takes n multiplications. All right, so now the denominator also requires computation. It requires QD. We need to multiply the matrix to the vector, and then multiply this vector and this vector. Okay, and the first thing is the matrix vector multiplication. So this is the Q is n by n, and then it's Q times D. So you can imagine how many iterations or how many computations we need here. When we multiply a matrix by a vector, we actually need to treat each row of this matrix as a vector, and then make an inner product of this each row with this vector D. Okay, so we will need to make, basically we're going to make n inner products, just like this. We'll need to make n of them. Okay, so in total we will need to have n square multiplications, and also for each row we're going to use n minus 1 summations, but there are n rows, so this is n times n minus 1 summations. And again, they are basically the same amount, and since multiplication is more expensive, we focus on the multiplication first. Okay, so that's why this part will require basically n square multiplications. This part requires n multiplications. So you can see this will be much more dominating, especially when n is large. Just always imagine that n is like in the tens of thousands or hundreds of thousands or over a million. That is usually the realistic case we consider. On the small side, for working more real industry problems, it could be just thousands of times larger than that. But at least it's several thousand, tens of thousands, at least this small. Okay. So as we said, this computation here takes the most of the computation. It requires n squared. Then multiply this 2 is n, and then this 2 is n. So the dominating part is this. Okay, so that is, we're saying that the dominating part is n squared multiplications, which is write it as multiplications, or the number of multiplications is this, plus the 2 inner products, so it's this. And the number of summations, as we said, is 2 times n times n minus 1 for the matrix vector multiplication, and then for the two matrix, for the two inner products of vectors, we have 2 times n minus 1. Okay, so that's the computation we need for this. Okay, and then next row, we're going to compute xk plus 1 equals to this. And this is simple. You just multiply this scalar to this vector, so it's just the n multiplications, and then add this, so that's n summations. So here we're going to have multiplications we need. Let me use this to be distinguished from the x. So I will need n multiplications, and for summations I need n of them. Okay, next, gk plus 1. So as we said, for quadratic function, the gk plus 1 is just the qxk plus 1 minus b. Well, so qxk minus plus 1, this we will need to make a matrix vector multiplication again. And that is supposed to be as expensive as this, right? Again, n square multiplications. But in practice, we don't really need to do that. Why is that? The reason is we can always just keep tracking this second line. Remember that if xk plus 1 equals to xk plus alpha k dk, we actually have the qxk plus 1 equals to qxk plus alpha k q dk. Okay, so what I'm trying to say here is that we can keep tracking this so-called qx because although I know that xk plus 1 is computed in this way, but I can store another vector which is dedicated for q times this vector, q times xk. So for example, I can call this vector the yk plus 1, yk. I always define this yk to be q times xk. So that means when I update xk in this way, I will also quietly update my yk. And this yk will be equal to, according to this formula, I will just get the yk plus 1 equals to yk plus alpha k q dk. But remember that we computed alpha k, q dk earlier for alpha k. So we can just store this in the memory. Besides multiplying this to this vector, we can also store it in the. Now we're going to add this vector, use this vector later to update my yk. And this update is simple because, as I said, this is a vector. Our yk is a vector. So multiply this scalar to this matrix, as to this vector, add another vector. This is really cheap. This is only on an order of n. Only need n multiplications. In contrast, doing this q times xk plus 1 requires n squared multiplications. As we said, if n is in the hundreds of thousands, then doing this will be hundreds of thousands times faster than doing this. Okay, so that's why this is a small trick that that can distinguish a very good programmer and a very bad programmer, because that the good programmer knows how to simplify the computations by reuse some of the things that are already computed, and this is the one of the examples. Okay, so that's one thing that you need to notice. So here we don't really need to do this matrix vector multiplication again. Instead, we can just quietly update this yk plus 1 in that way, and then subtract the b, we'll get the yk plus 1. Okay, so here, if we do it carefully, we know that this will only require, this part will at most require n multiplications for updating the y. So number of multiplications is again n, and then we need the summation and subtractions, and that should be n for the update here, and then another n for the subtraction here. So that's 2n of them. Plus or minus, it takes 2n in total. So plus and minus basically takes the same time. So we don't distinguish them. Okay, and next, let's see the beta k. So beta k, we're going to use the same trick. The qdk is something we already computed here, so just keep it here without recomputing it, and that is just a vector, and we just need to multiply this vector and this vector. So we don't really need to do that again. We just store this scalar and reuse it here. And for the numerator, we need to redo the computation because this is the vector. This vector that we already computed, and this is another vector. So we can just make a inner product of two vectors, and that is again just again it takes n multiplications, and we also need one division. We need to divide this number by this number, so that is n plus 1. But it's really just one more division of two scalars. That's really cheap. And also we need the summations, which is n minus 1. So remember that here I didn't really need any computation to get this. As we said, we can compute this one when we were trying to compute alpha k and store this as a scalar in the memory and then reuse it here. Okay, so that's this computation beta k. And then next, let's say we get the dk plus 1. So for dk plus 1, this will be a simple update because dk is a scalar, we just need to multiply the beta k to the dk, and then actually subtract the gk plus 1 from that. So again, the number of multiplications is just n, and the number of summations or subtractions is n minus 1. Okay, so this will be our total computational cost. We do need some little bit more memory cost because of storing this yk and also store this number here and store this vector. It takes a little bit more memory, but that's usually fine because the memory is pretty sufficient nowadays, and this is just the scalars, and they're not really these are vectors. They're not really matrices, so their size is just the same as those things. Okay, so if you can store 3 of them, storing 5 of them shouldn't be a big issue. Okay, so that's all the computations that we need, and as we said, the multiplication will dominate, and you can see the multiplication here takes n squared. We usually write this n squared. Big O n squared means that it's on this order of n squared, and this will be just n. So this is just O(n) multiplications. So I'm only counting the multiplications so far. And also this is O(n), and this is O(n), and this is O(n). Okay, so only the first one is n squared, and there are another 4 n's. But as we said, n squared is much bigger than n, since n itself is on the order of hundreds of thousands. Okay, so this is dominating part, and the overall the dominating cost is n squared. As we said, this is the most expensive part. Others are much less compared to this. Okay, so you can see that the computational cost for each iteration is in general n squared. Okay, and then we need n iterations, so total that is n cubed. Okay, because with each iteration we need this, and we need n iterations in general, so the computational cost is n cubed. Well, some of you still remember that we said taking the inverse. So let me first say that the total cost, I'm only counting the multiplications, is n squared times n, so it's n cubed in general. But remember that taking the solution to this quadratic function, the minimizer for this quadratic function is qx star equals to b. This is the only point that makes the gradient equal to 0. And this x star is just the q inverse times b. Okay? Well, and then this q, taking the inverse of a n by n matrix q is generally n cubed. Okay, and it seems that we didn't really gain anything because taking the inverse directly will require n cube computations, and doing this conjugate gradient method, we still need n cube, and that doesn't seem to save anything. Well, the trick is, first of all, taking the inverse of a matrix, that is really the n cube. What I mean by that is that it doesn't matter what this Q matrix is. This is the computation that we actually need to use, and there will be some small constant multiplied to that as well. So it's not just n cube; it could be 5 times n cube, or 4 times n cube. So that's a large. But in comparison, or n cube came from 2 things. One thing is that the n squared used to compute the q dk. Okay, but remember the q dk is just a matrix vector multiplication. You just say that how much we need to compute this thing. Well, in practice, although this q is extremely large, as we said, is the dimension n is hundreds of thousands, or even much bigger, the actual q matrix here is really sparse, in the sense that it has, for each row, it doesn't really have n non-zeros. It could just have a few non-zeros. Okay, what I mean is that if you treat this as the Q matrix, n by n matrix, this side is n, this side is n, and if each row, you could only have few non-zeros. It only usually looks like this, very sparse. Okay, this kind of matrix is called sparse. So what does this help us? Is that when you multiply this Q to some vector D here, you can see that when you multiply each row of this matrix Q to this vector, you don't really need to do this, do a real vector by vector multiplication or inner product of two vectors, because for each row there are only few non-zeros, and you just need to multiply the corresponding non-zero vectors to the corresponding values in the D, not the entire row. Okay, we don't really need to multiply the entire row to this D, but only few of them to the corresponding values, and that saves a lot. So for each row, we don't really need n computations. Maybe only need, even n is super large, in hundreds of thousands, the actual number of multiplications you need maybe just 5 or 10 or 20, something like that. Okay, so that is why this n squared is not really n squared, but probably just n, or 5 times n, or 10 times n, or 20 times n. Okay, that is much smaller than n squared. So that's one save. One how we can save computation. The other thing is that we said we need to run the algorithm for n iterations, but in practice, it converts much faster than n iterations. Usually we need just half of n, or even less, even fewer iterations to converge. So that also saves a lot. Okay, so in practice, the actual computation for the conjugate gradient method maybe just it's usually less than n squared, sometimes even smaller. Okay, so that's why it is big save. Although it looks identical to the directly inverting this matrix Q, but in practice, it is much more efficient. Okay, so after this, I hope you have some idea that the conjugate gradient method, although we analyzed its computational cost for each iteration of the total cost, but I will just give you a more explanation that why it is actually much faster than this. And this is also the reason why the conjugate gradient method is used to solve a quadratic problem like this, because in practice, the quadratic problem usually came from finding the solution of a linear system. So I'm going to write here. So remember that in practice, most of scientific computing problems can be written as a big linear system. Ax equals to, let me use another notation. Ax equals to say vector c, and this A is extremely large. Okay, this A is extremely large. Well, as we said, this A can be hundreds of thousands by hundreds of thousands. So the actual purpose, or the original purpose to solve this X used to be for X. And instead of doing this, you know that you can just say that X equals to A inverse times C. Let's say A is a square matrix and invertible. And it would say that my solution is just this. Well, in practice, that's not what people do. So what actually is done is that you consider the minimization problem of this Ax minus C squared. And apparently this is objective function is always greater than or equal to 0. If you do have a solution such that Ax equals to C, then the minimizer should be that solution. Right? The minimizer of this problem is the solution of Ax equals to C. But you look at the objective function here. This is our objective function. If we break the square, we'll see that this is nothing but the 1/2 times x transpose A transpose x, A transpose Ax, minus C transpose Ax plus 1/2 times C squared. Okay, so this is basically like A times X minus C, and you take the square, you have the x squared minus 2c times ax plus c squared, and you have 1/2, then just everything divided by 2. And this ax right now is the vector ax, and this square of this vector ax, and that is just it's just the inner product of ax and the ax, and this can be also written as ax transpose times ax. Okay, and you put the transpose inside, it will be giving you this will be giving you x transpose a transpose ax. That is what this term comes from. And the interacting term is this. So it's like this c times ax. And then you have this. This is a constant. Once you have the c, this is a constant. So this is a constant which doesn't affect your the choice over minimizer. And you can see that this is just this form. Compare this one and then this one. The only difference is that this is the Q matrix, which is here. This C transpose A, I can rewrite this term. The C transpose AX can be written as A transpose C times X. Okay, and this A transpose C here is the B. Okay, so this, as we said, this A transpose A is the Q matrix, and this A transpose C is this B vector. Okay, so it's like you're given this matrix, you have the A, C here. So you can construct this matrix and this A times C, or this A transpose C as the vector, and you are just minimizing. You're minimizing this. So minimizing the least squares. It's the same as minimizing this quadratic function, and it's the same as solving this linear system. Okay, so conjugate gradient method was actually developed to solve this, but because solving this is equivalent to finding the minimizer of this quadratic function, and that is the version of conjugate gradient method we saw here. We just saw in this optimization context. Okay. So now you basically give you no motivation why we study conjugate method. It is still the state of the art, even it was developed about 50 years ago. It's still the state of art. It's still the fastest algorithm, that one of the fastest algorithm we see that we use in practice. Okay. Okay, here is just a summary of what we had in the previous slide. We said the most expensive computation is QDK, as we showed. That it requires n-square multiplications and also some summations, but we said this is the dominating part. Again, for each iteration, this is done for one time only. Okay, although it appeared the QDK appeared several times, but actually we only need to do it once. Okay. And then this is the one thing that we mentioned to save the QDK for computing the GK, since the GK since it's not GK, it's this one. Yeah, this GK is actually updated in this way because the xk, because of this step, and we said this step you can multiply the q on both sides and we get this, and instead of really storing this yk plus 1, we can just subtract the b on both sides for this equation, and we know that this part will give us just gk plus 1. This part just gives us gk. So actually we can just directly update the gk plus 1 using this. Okay, gk plus 1 using this instead of storing another y. Okay, this is also some small trick that can reuse this thing to compute it. So the only thing that the only expensive thing we computed is this QDK for each iteration. Okay, but all those iterations, only this one takes n-square. All the others should be just n. Okay, so now finally we need to show that the the decays we constructed along the way of conjugate method are actually Q conjugate. Okay, so that's the proposition we're going to give here. The directions d0, d1 through d minus were generated by the conjugate method are this Q conjugate. Okay, so remember that what we need to do is to show that for each dk plus 1, it needs to be Q conjugate with all the previous dj's. So I need this to be 0 for all the j's from 0, 1 to k. Okay, I need to show this is true for every k. Okay, and again, similar as before, we're going to prove this by induction. First to show that d1 is Q conjugate with d0, d0, and then we make this as a induction hypothesis and then prove the next decay. Okay, so for the first one, we need to show that this is equal to 0. And the reason why this is true is because the d1, remember that the d1 was updated according to this last formula. So d1 should be equal to negative g1 plus b0 d0. Okay, so that's this. Okay, and why this is equal to 0? It is because of the beta 0 we chose. We set our beta 0 as this scalar. Okay, and this for k equals to 0, on the right side we just have g1 qd0, and denominator is d0 qd0, and that is exactly the one that makes this quantity equal to 0. Okay, so that's the choice for beta 0, and that makes it 0. So we have the first one for reduction as a starting point of a reduction. And now let's make the reduction hypothesis. So assume that at the iteration, when we get the decay, all the d vectors from d0 to dk are Q conjugate. And assuming this is true, let's show that dk plus 1 is Q conjugate to all of them. Okay, and that is the one we're trying to show here. Okay, now let's see why this is true. And it requires several facts that we have developed earlier. The first one is the way we constructed the decay. Remember that we constructed the decay using the negative gk. So originally we have dk plus 1 equals to negative gk plus 1 and the beta k dk. But now just the decrease k by 1 is still true. So dk was related to the gk and dk minus 1 in this way. That's the one that that's the definition for decay. So that's one thing that we know. The second thing we know is that the gk plus 1 is related to gk and dk in this way. Okay, and the reason is we know that xk plus 1 is related to xk and dk. This is our update rule. And then we multiply the q on both sides and subtract the b. Then we'll have qxk plus 1 minus b. And on the right hand side, we also have qxk minus b plus this alpha k q times dk. Okay, and then we said that this thing here is just the gk plus 1, and this thing is just the gk. So that's why we have this one here. Okay, that's the second fact. The third fact is one of the lemmas we showed earlier. Each gk is perpendicular to the gk plus 1 is perpendicular to d0 through dk, right? That's the one, the lemma we proved in the last lecture. So this is equal to 0. And lastly, we're going to show that gk plus 1 is perpendicular to all the previous gk's as well. So gk plus 1 is perpendicular to g0 through gk. And the reason for this is because, remember that the dk, the gk and the dk are related in this way, this first way. So that means the gk is a linear combination of dk and dk minus 1. So if gk relates to only as a linear combination of dk and dj minus 1, but j is less than or equal to k. So that means this one will be a linear combination for some d's and up to dk. Okay, the last one is this one. The last one is gk, and it is can be written as dk linear combination of dk and dk minus 1, like this one here, using this one. But we know from the third one here that the gk plus 1 is perpendicular to all the dk's up to all the dj's up to j equals to k. And this is written as a linear combination of those things. So it is still perpendicular to this. That is why this is also equal to 0. Okay, so not only this is equal to 0 for j less than or equal to k, but also this equals to 0 for j less than or equal to k. Okay, so these are a few facts that we need to prove the next dk plus 1. Okay, so remember that we want to show that the dk plus 1 q dj is equal to 0 for all the j less than or equal to k. And by this, we can show that dk plus 1 is perpendicular to, or is q conjugated to all the previous dk's. Okay, so to show that, let's first recall that the dk plus 1 was updated by using the gk plus 1 and dk in this way. This is how we update the dk plus 1. And to show that it's q conjugate to dk with dj, we just need to multiply this to q dj and see what happens to this. So there are two cases, either that j is strictly less than k, or j is equal to k. So there are only two possibilities. So for j is less than k, that means j is 0, 1, 2, up to k minus 1. What happens is this quantity here is multiplied to the q dj, but q dj, as we showed in the previous one, the q dj is related to the g. It's a linear combination, can be seen as a linear combination of the gj plus 1 and gj. Okay, so from here, I'm going to get gj plus 1 equals to gj plus alpha j q dj. Okay, and then we can just write the q dj equals to gj plus 1 minus gj divided by alpha j. Okay, we can replace by that. The only small issue here, possible issue here, is that if the alpha j is equal to 0, okay, what if that happens? If alpha j equals 0, let's see what happens. It means this will be 0. This will be 0. And if this is 0, that means alpha k plus 1 is just equal to alpha k. Xk plus 1 is just equal to xk. Okay, the only chance that this could happen is that we already got the solution. We already got the true solution. Okay, and by that time we should already stop. But otherwise, as we said, we'll just keep updating this, and as long as we're updating xk, this term cannot be 0. So alpha j will not be 0. So feel free to divide it. Okay, the alpha j will be non-zero. And as we said, we're going to replace the q dj by this. But remember that the j is less than equal to k minus 1. So that means the right-hand side can involve all the j's up to all the g's up to gk. Okay, so this side could be only involve or can be considered as a linear combinations of G0 up to Gk. Okay, but remember we showed earlier that the Gk plus 1 is perpendicular to all the previous Gks. And now this thing is some linear combination of G0 through Gk. And that means this has to be equal to 0. So the inner product of these two has to be equal to 0. Okay, that's the case where J is less than K. Okay, J is at most K minus 1. The second case, as we said, is J equals to K. In that case, this J is just equal to K. And now we actually need to multiply this to dk. So we replace that dk plus 1 by this, and then keep this qdk here. And let's say if this one is equal to 0. Well, this is exactly the reason why we chose the beta k in the way, as we showed earlier. The beta k was chosen in this form, and that is exactly the number that makes the combination we saw later as 0. Okay, that's the beta k we saw here. So actually we can see this by solving for this beta k, because we can combine this and move to the right, and then we have this thing multiplied to the beta k. So I just need to divide that number. So you can see that is beta k dk transpose q dk equals to, I have the gk plus 1 transpose q dk. Okay, and I just need to divide both sides by this quantity. Okay, and again, this one is non-zero. The reason is this q is positive definite, and this whole thing will be just the square q norm of dk. And unless d is a zero vector, this will be always non-negative. Unless d is 0, this one is always positive number. Okay, and d cannot be 0. The reason is d is the conjugate direction. As we showed earlier, that d is the conjugate direction. It's linear independent with other dk, so it has to be non-zero. This has to be non-zero. Okay, it has to be non-zero. Okay, and now we have shown that for in either case, j is less than k or j equals to k, we can show that this quantity here is equal to 0. Okay, so I forgot here, this should be equal to 0 for all the j less than or equal to k. And by this, we complete the proof by induction. We show that if dk is d0 through dk are q conjugate, then the dk plus 1 will be also q conjugate with respect to all the previous dk's. And that finishes the last thing we need for the conjugate gradient method. So in summary, what this algorithm is, we need to implement the conjugate gradient method for solving the quadratic, for minimizing the quadratic function above here. We just need to iterate the steps here. And the alpha k is the step size. Xk is updated from xk plus 1 is updated from xk by adding alpha k times the descent direction, or the conjugate direction dk. And then we compute the gradient of fx, gradient of f at xk plus 1, we get the gk, and then we compute this parameter beta k, and use this beta k to get the next conjugate direction. And then we repeat. And we said that these dk's are actually conjugate directions, and according to the property of the basic conjugate gradient algorithm we showed earlier, this method will converge within n steps. That means at iteration n, when x equals to n, this xn must be solution, must be the minimizer of this fx. Okay, and that is the latest case. It could happen earlier, as I said earlier. Okay, it could happen earlier than iterations. Okay, so this is the conjugate gradient method. So far, we have considered the conjugate gradient method for solving the quadratic function. But in practice, it can also be used for solving non-quadratic function. That is it's also very common in practice. Not all the functions we're trying to minimize are quadratic functions. Or if it is not a quadratic function, the conjugate gradient method is not going to guarantee a convergence within n steps. And also there are some other issues. For example, we're going to find the step size alpha k, and this alpha k probably will need a line search because it doesn't have a closed form now. The steeply descent step size doesn't have a closed form when f is not quadratic. Okay, and in this case, we need to do the same thing as we did for gradient method. We need to for every xk and dk, given xk and dk, we need to find this alpha by minimizing this line search function. This is the function of alpha, a scalar alpha. So we can use a secant method or something like this, like that, to solve for this minima, to solve for this best step size alpha k. Okay, and also the beta k does not have a closed form for that either, because previously we got the beta k when the function we're trying to minimize is quadratic function. And then that's how we obtain the beta k. But here, I think there would be a negative here. But here, the issue is that it's not a quadratic, so we don't really have the beta k formula like this one, because the q is the q in the quadratic function, but it's not a quadratic function. This q is changing every time, right? Because this q is actually somehow like the Hessian matrix of the function f at the point xk, and that's changing. So we cannot really have this beta k formula. Okay, well, I said it here. So if it's quadratic function, the Hessian, so we said if it's quadratic function fx equals to 1/2 x transpose qx minus b transpose x, we know that the gradient f is clear, which is just xk minus b, and the Hessian is just q. But if it's not a quadratic function, the Hessian may not be a constant q matrix. It could be changing. Okay, now what we should do in this case? There are several ways to modify the formula for the beta k so that we can still update the beta k. Okay, and the first one is called the Hastings-Stifel formula. So what they do is to try to get rid of or try to eliminate using avoid using this q d to k. So they said that the q is changing every time. Okay, so they're trying to avoid using this. The first formula, Hastings-Stifel method, is replacing this q dk by this, okay, by this quantity, and this is it has some idea. It has some motivation because previously we showed that for the quadratic case, the gk plus 1 was related to. So I hope you can still remember that the q dk is equal to this minus this divided by alpha k. So now I have the q dk on both numerator and denominator, so I can replace that by this gk plus 1 minus gk. And that is the reason why I've had this one here. Okay, and also the denominator is replaced by this, and the two alpha k's are cancelled. We cannot really cancel this vector with this vector because we're going to multiply this vector to another vector is an inner product, so we cannot really cancel these two. But the alpha k, which is scalar, it can be pulled out and then it can be cancelled. Okay, so that's the first formula. The second is a Pollack-Ribian formula. That is, the numerator doesn't change, but the denominator is replaced by the gk square. Okay, it's replaced by the gk square. That's the second formula. The third one is the Fletcher-Reeves formula, and that's also replacing the numerator by the gk plus 1 squared. Okay, so they are all kind of replacement for the original formula in order to avoid using the dk, qdk, but they all reduce to the same formula they all reduce to the same formula like this one when we're actually working on quadratic functions. Okay, so these are all generalizations of the formula here. Okay, so what I'm trying to say here is that if you are really working on a quadratic function, don't worry, these three will reduce to the formula here. Will reduce to this one. Okay, and some remarks. So we said first, when all these three modifications will be reduced, we reduce to the original conjugate gradient method when f is quadratic. So they still want to keep the optimality of the conjugate gradient method when applied to quadratic function, which is the one original purpose for the development of conjugate gradient method. Second is that since it cannot guarantee convergence within n steps, we probably will expect to run more than n iterations, and it is usually we need to do this so-called reinitialization of the dks, because after n iterations, where n is the dimension of the problem or dimension of the x, we probably run through all the conjugate directions. So we need to reinitialize the dk to the current negative gk and repeat the procedure. Okay, so that's why reinitialization may be required. And also the line search accuracy will affect our performance. This is line search accuracy. You can do it very accurately, but it's expensive to do this. I need to find the optimal alpha, and that requires taking the gradient of this multiple times. That can be expensive. Actually, you can show that taking the gradient of this requires a q times this. Q times this minus b, and the q times this is a matrix vector multiplication, and that is n squared of the computation in general. That makes it expensive. So you can either spend more time on this, and hopefully you can get fewer iterations, or it can be a little bit less accurate here. Just run this second method for a few iterations. But hopefully that after you update this alpha k, you can immediately quickly move on to the next point and compute the new descent direction or conjugate direction. And that probably can help improving the overall performance. Because as I said, its overall performance is not only the total number of iterations, but also the computational cost you spend for each iteration. And the line search takes some computations during each iteration. So you want to keep that computation complexity low. Okay, in some experience, when you use this algorithm, usually there are very mature software packages in Python or MATLAB or even other softwares. So they all implement these methods, and you can use the Hastings-Stifel method when the line search is not very accurate, and you can use this one when the GK is bounded away from 0, and you can use the Fleischer-Rives method for better overall convergence. So you can try all of them in practice. Okay, so this completes the discussion on conjugate gradient method. Okay, next we're going to talk about an important class of optimization methods called Quasi-Newton method. So the Quasi-Newton method is a modification of the Newton's method. So before that, we first recall the Newton's method was set to this update rule. The xk plus 1 is computed or is updated from xk by doing this operation. This is a Hessian of f at xk plus 1, so xk, and we need to take the inverse of this and then multiply to the gradient f at xk. Okay, and this we usually call it hk. Okay, this is the Hessian of f at xk. This is the matrix n by n matrix. This we usually just denote by gk, which is n by 1 vector. It's an n-dimensional vector, just like x. Okay, so this is Newton's method. Well, what is Quasi-Newton method? This is trying to overcome the issue with the Newton's method, because in Newton's method, we need to compute this thing, and taking the inverse of this matrix, or at least we need to solve for the vector. So we can call this whole thing to be the negative dk. Okay, and then we need to solve the negative dk from the hk. Sorry, let me just try to reset this part. So I'm going to solve the dk from hk dk equals to negative gk. So suppose we are at xk, we can compute the gradient gk and the Hessian hk, and then to solve for the vector dk, and that's my dk. Dk will be, by solving that, my dk will be equal to hk, negative hk gk, or in other words, negative dk will be equal to hk times gk. Okay, and usually this is how we get this vector. And then once we have that, we can subtract the dk or minus dk from the xk. So that will be xk plus 1 equals to xk plus dk. Okay, so but anyway, the key is to solve this linear system. And that solving this linear system is not easy, as we showed before. The conjugate gradient method was almost dedicated to solve this kind of problem, because this could be very large matrix. Okay, so solving a inverse of this matrix is not really practical in real world. So that's why the Newton's method is not really popular in practice. Although it has very nice convergence property we showed before, it is converged at order 2, and let's say it's considered as a very fast convergence, but the per iteration cost is too high. We need to spend lots of expense computations for each iteration. And that is a drawback with the Newton's method. And there are several other drawbacks with Newton's method we discussed earlier, but this one appears to be the most difficult one. Okay, and that's why people came up with this Quasi-Newton method, is trying to approximate the inverse Hessian. Remember, the inverse of this Hessian matrix is the most troublesome term. Okay, or this term. This is the most troublesome term. So we replace this inverse of the Hessian by some hk. So this hk, you see the notation, this hk is different from this hk. We will have the superscript k, that means the Hessian matrix. So once you have the xk, you can compute the Hessian. But this hk is some matrix that we're using to approximate the inverse of the Hessian. Okay, so if we can really do this, then our update rule will become very simple. The xk plus 1 will be updated from xk minus alpha k is the step size, and this hk, the gk is what we had earlier, and this hk, if we were using the Hessian inverse of the Hessian, then this just becomes the Newton's method. If we further set alpha k step size alpha k to be 1. But right now we're replacing this Hessian inverse of the Hessian by this HK matrix. And the matrix HK, when you multiply these two, that's simple. It's just a matrix vector multiplication. That's supposed to be simple. Okay. Or in other words, we're actually doing the standard gradient descent method with this step size, with this search direction dk set to negative of hk gk. Okay. So the key is in this hk. How do we get this hk so that it can approximate the inverse Hessian? Okay, and if it is, you can find a very good approximation, then this method is can potentially behave similar to the Newton's method, and that means it can converge really fast. Okay, so that was the motivation for the Quasi-Newton method. And now let's see why. Well, what is good for this? What is good with this kind of step size? The first thing is, recall that it is equivalent to a gradient descent algorithm with dk, descent direction dk set to negative hk gk. If this hk is positive definite, then this dk is guaranteed to be a descent direction. And the reason is that, remember, for this dk to be a descent direction, we just need to show that for step size alpha small enough, going along this direction will give us smaller function value, right? So we'll say that I have an xk plus 1 equals to xk plus alpha dk. Okay, it's a descent direction, or it's a descent method. If f of xk plus 1, according to the definition of xk plus 1, is just f of xk plus alpha dk is smaller than f of xk when this alpha is not too large, right? That means your next point will have a smaller function value than the previous one, and that makes this function value decreasing, and that's basically aligned with our goal to minimize the function f. Okay, and here, if we set dk to be negative hk gk with positive definite matrix hk, then it's guaranteed to be a descent method. Okay, that means this will happen. And to show this, we have seen this kind of proof before. To show this easy, you just define the line search function phi of alpha, which is just a function of the scalar alpha, and then we set this to be f xk plus alpha dk. Okay, and then the phi 0 will be just f of xk. And if we draw the picture of this phi, this is the alpha, this is 0. So this is the phi of 0. And this basically, we're looking for the function value along the line starting from x0, or along the ray, starting from xk, and go along the direction dk, and the step size, alpha is the step size. So we go along the direction. If we can show that the derivative is negative at this point, then it will go descent like this, and maybe eventually it will go up, but we don't care. At least for alpha small enough, the function value should be decreasing. Okay, so the only thing we need to prove is to prove that the phi prime is equal to 0 at 0. That means we need to prove this is smaller than 0. And the question is if this is true. Okay, so recall that our dk was set to negative hk gk in the Quasi-Newton method. And now to compute the phi prime of alpha, we have done this multiple times. This is just the gradient f of xk minus alpha hk gk, since this is our dk now. And then we need to multiply the derivative of the inside with respect to alpha due to the chain rule. And the inside multiply, what is multiplied to alpha? Let me just replace this. This is actually just a negative of hk gk. Okay, so when I multiply the gradient of the inside with respect to alpha, I will get negative hk gk. Okay, and now we can see that what is phi prime at 0? We just need to set alpha equal to 0. But the alpha equals 0 means this one here is just 0. Okay, so that's what we're going to do, just set to 0 there. So the phi prime at 0 is just a gradient f and xk. The others become 0 times negative hk gk. Okay, I pull out the negative and realize the gradient f at xk is just gk itself. So I have just gk transpose h gk. hk gk. Well, as you can see, if hk is positive definite and g is not 0, g is not 0. Well, even if g is 0, already reached to the critical point, and they already give us the solution or local minimum or something like that. So we in practice people usually stop there. So but if it's not 0, that's when we can still make progress. But when gk is not 0, hk is positive definite, that means this thing here will be strictly positive, and the negative of this will be strictly negative. So that's how we show that the phi prime at 0 will be negative if the hk is a positive definite matrix. So that is also one of the principles that we want to follow when we design the Quasi-Newton method. We want to set up this hk so that it's always a positive definite matrix. Okay, so the proof I gave here is just the same, exactly the same idea. It just express out what this line search function actually is. And from there, you can show that by realizing that xk plus 1 is just xk minus this, so I can take the Taylor expansion of this f, because this xk is nothing just but this. So I expand this at the point xk, I'll get these terms. And if I want this whole term to be less than, so this is the 0th order term, this is the first order term, you can try it by yourself, it's just the first order term. This is the second order term, and it is supposed to be little o, small o of alpha. So that means if alpha goes to 0, this term will go to 0 faster than this term. Okay, and so if you want this whole thing to be less than f of xk, that means you want this whole thing to be less than 0, you can just show that this part is positive. If this is positive, then when alpha goes to 0, this whole thing will be dominating. This term will be a negative term that is dominating this term. And that will make the sum of these two circle terms less than 0. And that will make this smaller than this f of xk. Okay? So this whole key is just this. Just make this less than 0. And when the hk is positive definite, gk is non-zero, then this is guaranteed to be strictly positive. Okay, and that's exactly the same idea as used in my written proof.